It's a different idea, and this idea started in around the year 2000 in our group, and it has been applied in many contexts. To simplify the exposition, I will deal with only the equality constraint, the problems with only equality constraints, but with an additional linear set. You can have inequalities, but they are linear. In fact, you can always transform a problem with general inequality constraints if you add slack variables, as I told you before. You change g of x less than or equal to 0 to g of x plus some z equals to 0, and z is greater than or equal to 0. So this can be done, and this approach can solve problems with inequality constraints also. The philosophy of inexact restoration methods is that you have, at each iteration, you have two phases. The first phase, you try to look at feasibility. There are some methods that, when you, at each iteration, you move from a point x to a point xk plus 1 by minimizing an approximation of the objective function, an approximation of the constraints. And then you restore this approximation to a feasible point. You have age of xk is 0, you generate an approximation that maybe it's not 0, age of xk plus 1 is not 0, so you have to restore feasibility in some way. And the idea, it incorporates this inexact restoration of the constraints. So given a point xk, the goal at this phase is to obtain another point yk that is simply closer to the feasible region. In this phase, you should improve the infeasibility of the iterate. This should be done. This cannot be done in any way. You should do this in such a way that the objective function is not radically worse than at xk. You can do this by taking yk close to xk. If yk is close to xk, the objective function may be worst, but it's not too worst, too bad. And in the second phase of one iteration, you have the optimization phase. So you are now at yk. Around yk, you should make a model of your objective function. You try to obtain a trial point zk with better objective function. You should do this without losing much of the feasibility that you got from the previous phase. So in the first phase, you get feasible, more feasible point without losing optimality. In the second phase, you get a more optimal point without losing much of the feasibility. And then you must have a globalization step. This is you should be able to control how these points moves by minimizing some merit function, and this can be done in order to assure global convergence, to converge independent of where you start. So you do this by measuring comparing this point zk that you get in the end of iteration with the point xk, and now you measure both infeasibility and optimality. If both things are good enough, you accept this point zk. Otherwise, you get a new point closer to yk, and then you accept this point closer and you repeat. So let me show you how this works. I have here this constraint, age of x equal to 0. It's this curve. The box is the screen, and these are the level sets of the objective function. Okay, so this is the minimizer. This is the feasible point with the smallest value of objective function. And I start at this point, any point inside the box, xk. And at xk, you have this infeasibility of 20. It's a very infeasible point. And maybe this is the level set of this value, age of x equal to 20. So the first phase, you try to get closer to the feasible region. So you compute this yk, so infeasibility measure decreases to 10. And, okay. In the second phase, what you have to do, you compute this point zk. So this is, look here that the objective function value at yk is larger than at zk. Okay, it's the more far away from the center of these circles, the greater the objective function value. So this is closer, and we find this point zk by minimizing the objective function or some approximation of the objective function, and along the tangent set. So here I'm at yk. I want to keep this feasibility. I want to keep the same level of infeasibility. At yk, the infeasibility measure was 10. I want to compute this zk with the same level of infeasibility. So I minimize the objective function along this tangent space. So I know that at least close to yk, this is a good approximation to this level curve here of age of x equal to 10. So I compute a first trial, zk, and okay, maybe the optimality is better, a little bit better, but I went too far away from yk. The feasibility is now not good. So my merit function test fails, and I have to reduce my step. So when I reduce here my step, and this point is not accepted also, so I reduce again. Then this point is accepted. The objective function value is small, and feasibility is, okay, not too bad. So this is my next iterate. So at this point, yk, the infeasibility was 10. At xk, at this xk plus 1 that I call again xk, maybe it's a little bit worse, 10.5. So I repeat, I compute yk closer to the feasible region. Its infeasibility measure is 5. I compute the tangent direction, and I give this long step zk, and this is accepted. Infeasibility measure is worst. It went from 5 to -7. It's more away from 0, but it's very close to optimality. So I accept this point. And I repeat again, I get yk closer to the feasible set, -2. I walk here to the zk, and you can see that I'm getting closer to the solution. So this method might work. And so why should you use this two-phase algorithm? And the idea here is that if you want, most methods, they deal with feasibility and optimality at the same time. Okay, such as the Augmented Lagrangian method, it deals at the same time. And maybe for some problems, for some classical methods, subproblems may be infeasible. This is true for the SQP method, where you linearize the constraints and you make the objective function a quadratic approximation of your problem. When you do this, maybe your subproblem is infeasible, then you don't know what you could do. In this case, this will never happen. And if you consider this, if you formulate a model of your problem considering optimality and infeasibility in the same sense, if your point is very infeasible, if you start with an xk without looking at infeasibility, the model of your problem will not be very good. Okay? You are making a model of your problem on a point very far away from the feasible set, So maybe this is not representative of the true problem. So if you in this idea you make the problem around you make a model of your problem around a point that is more feasible, and this is very interesting. It may be the case that one of the goals may be much easier than the other. Maybe your problem it's easy to deal with the constraints. The constraints are very much easy, but the objective function is very difficult to compute. Maybe it's a very expensive objective function, and so with this idea, you only you can exploit this structure. When you mix together objective function and constraints, you lose this idea that the constraints are easy to compute, because you are always computing them together with a difficult function. So you can't explore this kind of structure, and it may be the case that the problem has a structure. When you think of the problems of these goals separately, so I am at an infeasible point, and I want to find a more feasible point. Maybe this is an easy problem. It has some structure, and in your application you can always find a feasible point, for example, closer to this one. This can be the case, so you can exploit this kind of structure in the problem. So there is not a general implementation of the inexact restoration methods. Typically, there are implementations for particular applications. This is because this method works well when there are these kind of structures that you are able to exploit. And this can be was done for this, at least for these 5 classes of problems. There are these problems in chemical engineering, where you want to find the electronic structure of some molecules, and in fact it has been exploited, this kind of structures, and this method works well. And Professor Yao Chinkaya from Australia, he had employed this kind of method to optimal control. For derivative-free methods, it has been used for bi-level optimization. So this is the case when you have to minimize a function, and one of your variables, to check feasibility of one of your variables, you should solve another optimization problem. So this is a 2-level optimization problem, and this has a structure that can be exploited. And in this paper that I will comment, we solved multi-objective problems. Okay, so this is the general idea of the method. Martinez's ideas for this method from 2000, they were very complicated, but in 2009, there appeared this paper by Andreas Fischer and Friedlander, and where they showed a very simple framework for an inexact restoration method. So you have some parameters here, and you initialize an initial point inside your box, your linear set, and you initialize a penalty parameter here. So the first step of an iteration, it's the restoration phase. You compute yk inside the linear set, such that the infeasibility measure is improved by a fraction. This r is a fraction, and the objective function can be worst at yk, but the difference is bounded by this term. Okay, so if you're getting closer to the feasible set, you can't lose much of this objective function violation. So this is the restoration step. The optimality step, you can solve a problem like this. You can compute, at least in their algorithm, The idea was to compute minus the gradient of the objective function and project it in the tangent space. Okay, so in the picture, I'm at this point yk, and gradient of the objective function is pointing this way. Okay, so what the algorithm does, it projects this direction in this subspace. So you get this point zk here. Okay, and so you should project in this tangent line, in tangent space, and you should keep inside your linear set. The problem here is that you are using only first-order information of your function. In this work, we incorporated second-order information of this method, and we can see that they are not making use of the Lagrange multipliers. So typically, we know that if we incorporate Lagrange multipliers, an approximation for Lagrange multipliers here, we are able to improve the performance of the method, and this is what we did in this paper. There are some other steps. The globalization step. You should compute the penalty parameter. So you have this is the merit function that we use, okay, to check if a point, to compare 2 points. So it's a convex combination of optimality and infeasibility. So if this convex combination is better, then you accept this point as your new iterate. But there is this parameter that you have to choose at each iteration, and you choose this parameter in this sense. You choose theta k such that this condition holds. This is saying that the parameter should be such that yk, the point more feasible than xk, is better with respect to the merit function. It's sufficiently better. This difference is less than this term. And now in the globalization step, you perform a line search. So you are at yk now. You want to compare this new point with xk. The point zk is yk plus dk. If you take this full step, tk equal to 1, you get this initial approximation that you should check. So if this new point zk is sufficiently better than at xk, you accept this point. Otherwise, you reduce this step size tk. So you can take here tk equal to half, and then you have a new trial point, and you check if this will happen. Since at yk this test will be accepted, if you take t sufficiently small, this will be accepted. Okay, and you also has to choose a step size such that the objective function decreases. Then you update your point. Your new xk, it's simply this new point, and you repeat. Okay, this is the Fischer Friedlander method from 2009. This is a simpler version than the original one. And what they were able to prove is this. The penalty parameter is bounded away from 0. Okay, so you are reducing this parameter theta k in each iteration, but if this was going to 0, you would have a problem. If this was going to 0, your merit function would not be looking at the objective function. You would accept iterates only looking at infeasibility, and this is not good. So if you have a result like this, you are sure that you are always looking at both objectives when you compare two iterates. This step size tk is accepted after a finite number of attempts. This is a convergence series. In particular, the term age of xk converges to 0. So this is converging to feasibility. Xk converges to a feasible point. And this sequence decay the sequence of directions, this converges to 0. This means that the linear AGP optimality condition holds. If you remember, the linear AGP was something like this. It uses here the projected gradient and projection on a tangent space. So, and it asks that this projection should go to 0. So, if you are able to prove that decay goes to 0, you in fact, this is an optimality condition. Okay, so this is important to show that a sequential optimality condition is satisfied. And in this case, it's the linear AGP that it's a good sequential optimality condition, and in particular, you get KKT points if you assume a weak constraint qualification, such as the CPG. Our idea is to replace the optimality phase with this subproblem. Here, if we chose HK as the identity matrix, you would get exactly the Fischer Friedlander direction. This would be the projection of minus the gradient on the tangent space. So it turns out that you can build here a quadratic model for your problem. So in HK, you could replace it with the Hessian of the objective function. So you would get a quadratic approximation of your function. Or you could, in fact, what we use in our implementation, we use the Hessian of the Lagrangian function. So we would be minimizing the Lagrangian function, and this works better. But in theory, it could be any sequence of uniformly positive definite matrices. So the idea was to use here the Hessian of the Lagrangian. Okay? And when we solve these two problems, we will have an approximation to the Lagrangian multipliers here for these constraints. So I minimize this function using any solver. It typically will return an approximation to the Lagrangian multipliers. So I can plug in this approximation to compute the next Hessian. Okay, and this will be a better approximation for the Lagrangian, and this sequence of multipliers will converge to the true Lagrangian multipliers. And for this to work, we have to make some corrections here in the globalization step. So as in the merit function, instead of looking for the objective function, we look at the Lagrangian function. So we have to check here improvement with respect to different multipliers, lambda. And at the line search, we also have to compare here with different multipliers. And the decrease of the function is replaced by the decrease in the Lagrangian. So you don't need to worry about the details. So as I mentioned before, in the original algorithm, if we get HK equal to the identity, we recover the original direction by the method. And if we choose the approximation of the Lagrangian multipliers always equal to 0, we in fact recover the whole algorithm. In our implementation, the Hessian, the matrix HK, will be the Hessian of the Lagrangian function using an approximation lambda k. And lambda k minus 1. And then the next lambda k is simply the Lagrangian multiplier obtained in the optimization phase. So here there's a picture that is telling you why in the tangent space maybe it's better to minimize the Lagrangian and not the objective function. So this is one phase. This is the constraint. I want to find the minimizer of this objective function that measures the distance to this point to this green line here. So I am at this point. This is a maximizer, so it's not a good point. So, but if I linearize this constraint, this point that was worst, it was a maximizer. I don't want this point, it's now the minimizer of the linearized version of the problem. Okay, this is the new constraint. So I linearize this constraint, and the solution will be at this point. It's the minimizer. But this is in fact a maximizer of the true problem. So this is because we are minimizing the objective function and not the Lagrangian. So maybe it's a good idea to incorporate information of the constraints on your objective function to avoid something like this to happen. In our implementation, we used a quadratic problem. For the subproblems, we need to find a solution of a quadratic problem, quadratically convex problem. So we use this method of Fletcher's, filter SD, and KLCPD.
Excuse me, in this example you put there, what would happen if you apply the original Fischer Friedlander algorithm? Would it stop at that point, or?
If I apply here the original, yeah, I think it would be stopped here. This will be a solution for him, for this problem. It would stop here. But this is only a toy problem, okay? It's good faith.
In this problem, the original algorithm would not get feasibility, or would it?
Would get what?
Feasibility?
Here, I think I'm assuming that this point is feasible. And I want here to get a point with respect to optimality. So I want to, I wouldn't move at all here. This would already be a solution. This would happen. And what we can, with this modification, with this improved version of the method, we can prove exactly the same as we had before, and we can also prove convergence of these approximate Lagrangian multipliers. Okay, it's the same as the augmented Lagrangian. Under Mangasarian form of it, every subsequence, this sequence is bounded, and every subsequence, every limit point is a Lagrangian multiplier. So for an application, we did these applications in multi-objective problems, and we consider this economics problem. It's the mean variance problem in portfolio optimization. The idea is that there is a portfolio, there is n assets that you are aiming, you can invest your money, and you want to build your portfolio. You want to know which assets you will invest your money. So xi will be the percentage of money that you invest in the asset I. So you must have this constraint. If you add you should invest all your money. You must invest a non-negative amount of money. And typically there are two objectives that you can minimize in order to choose your portfolio. Here it's the vector C is the average return of an asset. So you can look at the historical data of the assets, and you can compute the expected value of the increase in the value. You can predict the expected value in the next month. So you want to minimize something like this. So this is the average return, the average loss that you get in this if you invest this money. And this is the risk in investing in these assets. So you can compute this matrix, covariance matrix Q of all your historical data, and typically this quadratic form here measures the risk in investing your asset. So you want to invest in an asset that has a very large expected return, or a very negative expected loss, and with a variance very close, very small variance, very close to 0. So this is why you minimize this. And for multi-objective problems, the notion of a solution is not a single point. So you can have something like this. This is the first objective that you want to minimize. It's the average return. And this is the second objective. It's the risk. Okay, so I want to have a point with a small value here and with a small value here. Okay, and these are all the feasible points. Okay, what's the solution in this case? Clearly, these points here are not the solution. Okay, because I can find points down here that has a smaller value of both objectives. Okay, so these points are dominated by these others. So the notion of solution is this curve here. It's called the Pareto frontier. Maybe it can be a discrete set like this, but typically it's a curve here. And these are the points that are not dominated by anybody else. Okay, so in practice, what you want to return this whole frontier. The solution is the Pareto frontier. But this is almost impossible to find in practice. Our algorithm typically returns one point as a solution. It can't return a curve. So what people that study multi-objective optimization, they try to solve the problem many times and try to simulate this frontier. The difficulty is to prove that you will cover the whole frontier here. Maybe if you solve the problem many times, you'll generate points here, and you'll generate points here, but you can miss points here. Okay, so it's a very, very tricky problem. Our approach to this problem, so in this economics problem, what this is saying, why this is the solution. So you want to invest at some point here. Okay, I have this. I have a guess, or maybe this is a good point. I want to invest my money here at this point. But this point is dominated by others, so you should not choose this point. And see here that if I choose a point in the frontier at this side, I will have a very, very low return. So the average return here is very high, but the risk is very low. So it's a conservative investor. He aims to have a very low risk, and he can have he doesn't need a too high return. And this is the other end. The return is very high, and the risk is very high also. So it has a very, very good point here in the average return he gets, but it's a very risky investment. So this depends on the profile of the investor. I don't know which one is best, so depends on your situation, and this is why this is the solution. So this profile of the investor should give you an idea of what kind of decision you want to make. So you can choose this beforehand. So you choose this point. I want to take a decision somewhere around this point. Okay, then what our algorithm does, it finds a point in the Pareto frontier closest to this chosen point. Okay, so this is reasonable. It's our approach to this multi-objective problem, but it only generates one point in the frontier. So it turns out that you can compute these points in the Pareto frontiers by solving a problem of this form. So it's a convex combination of both objectives, and this gives you a point in the Pareto curve. there are some assumptions here that you have to take for this to hold. But typically, if you choose one alpha here and minimize this problem, you will get a point on the Pareto frontier. There are some technicalities here. Maybe you can't get every point on the Pareto curve, but at least this will be some point in the Pareto frontier. And so this will be the constraints of our problem. I want to minimize this distance from x. I want x to be closest to this decision xd, and this is the constraint. I want x to be a solution of this problem for some alpha. Okay? This is what it's written here. So now x is my variable. I want to minimize the distance of x, distance squared, to have differentiability. And this is the constraint. X should be a solution of this problem. Okay? But I don't know alpha either. Okay, alpha now is also a variable. So I should choose alpha, and for every time I choose alpha, I get an x that is a solution for that, and I can check if that x is close to xt. If this is not the case, I can move to another alpha, compute this, get the x, and see if this is closer to xt. It's so formulated in this sense. You can see that it's difficult to solve this with classical nonlinear programming solver. The classical approach to solve a problem like this is to reformulate the lower level Pareto problem by its KKT conditions. So it would be something like this. Let me write it down. So I want my alpha and my x to be solution for this minimization problem. So instead of asking this, I will formulate this as the necessary optimality conditions for this problem. So it would be something like this. Alpha is fixed, and for this problem, x is the variable. So it would be something like this. This is the derivative of the objective function. And at the solution, that there should be Lagrangian multipliers associated to this constraint. So there would be lambda 1 times the derivative here, something like 1, 0, up to lambda n 0, 1. And here there's something wrong here. There's only one constraint. This is what we get. There's a lambda, and this is the derivative. Vector of ones. And here I have n constraints, and I should have something like lambda 1 minus 1, 0 plus lambda n minus 1. Okay, something like that. This should be 0, and complementarity should hold. Lambda I x I should be 0. This lambda I should be non-negative. Okay, this is the first order optimality condition for this problem, or maybe something similar to this. So what I can do now, I can formulate a nonlinear programming problem. I minimize alpha x in alpha and x, this condition, and I add here these constraints. Note here that lambda, lambda i's and lambda, these are also constraints, these are also variables for the problem. So I plug it all in, and I try to find a feasible point for this problem, such that this first order optimality condition holds. So the Lagrange multipliers can be variables now. And this is the classical approach for this problem. The problem is that you are not exploiting the structure of the problem. At this problem, the x should be a minimizer, but since you are looking only at first order optimality condition, you can have a saddle point, you can have maximizers, and it won't make any difference, and maybe you can converge to the wrong solution. So you are not exploiting the structure of the problem, and this can go wrong. It's an approximation. Yep. So with inexact restoration techniques, you can exploit those structures. So you have an approximal an initial point, xk, alpha k, these are the variables, and at this point you need to find a restored point. So initially this xk, maybe it's not the solution associated to this alpha k for the lower level problem. Xk is not the Pareto point associated to alpha k. There's no point to assume that. So the restored point, I will find this point, this should be closer to the feasible set. So yk should be closer to being a solution associated to alpha k. And I compute this restored point by solving this Pareto lower level problem for this fixed alpha k. When I solve this, I get yk. And in fact, if I solve this to get an exact solution, I get a feasible point for the original problem. Okay, the yk will be a solution for this problem, and this is feasibility for the original problem. Okay, so I can get in this way I can get a point closer to the feasible set. And at the optimization phase, what we want to do is minimize the objective function, but we don't want to get far away from the feasible set. So I am at this point yk alpha k. I want to walk in some direction that changes y, and in some direction that changes alpha in some sense, but I want to find this direction that minimizes the function, but I don't want this direction to go far from the feasible set. So when I walk along these directions, this new point should also be solution for Pareto points associated to this new modified alpha. And this is very hard to do. I don't know how we should do this, but one way now is to look at the KKT conditions. So I write down the KKT conditions for this problem, and it has some, it's that thing that I written, and it has some formulas like this. It's an equation, depends on the variables x and alpha, and depends on the Lagrange multipliers lambda. This should be 0 with some non-negative constraints also. So maybe this yk, it was a KKT point, and what I want to do is to move along this direction, move x, move alpha, and move lambda in such a way that this is approximately satisfied. So I build the tangent direction, I build the tangent set of these KKT conditions. And this is something like this. Okay? The h of x equals 0, and I compute these derivatives, and I get something like this with some bounds for this direction. And so if I walk along this direction of x, alpha, and lambda, I will be on the tangent space of the KKT conditions. So maybe this is good enough to say that I'm not getting away from being feasible for this minimization problem. And here I can minimize the objective function. It's a quadratic function. So this yk plus the d, this is my new x. This should be close to xd. And Note here then that I must keep an approximation for the Lagrange multipliers here of the original problem. So I have this lambda, I should have an approximation, and this tells me how I should update the Lagrange multipliers approximation. So I tried this point here, new point, yk plus d plus dd, alpha k plus dd alpha, and lambda k, and I check if the merit function is improved. If not, I reduce t, and I can do the same algorithm that I mentioned earlier. So there are some test sets.
Excuse me for a second. I think I'm missing something quite fundamental here. So suppose I have this candidate solution xd to start with, and suppose now that I say, okay, I will solve the problem you have there on top for a grid of different values of alpha. So I will take alpha from 0 to 1. I will take, let's say, 20 values of alpha, and when I'm done, I take, let's say, so I will get points in the Pareto frontier, and then I will get the one that is closest to xd in some sense.
So you choose a lot of values of alpha,
yes.
Choose x. Okay, so you are not minimizing anything. You are choosing at random some alphas and getting the x, feasible axis, and you get the best one. This is not a good way to minimize the function, but okay.
But what function are you minimizing then?
This one.
Just be closest as to b.
As the x. The problem is that you don't have the x along the Pareto frontier. You have only the alphas. So when you have an alpha, you don't know where the x will be, but that's what you want to minimize. Where alpha, the distance of that x to the decision xd. Okay. This is a little bit hard to follow. It was very hard to implement this, and I got confused a lot with this. But if you can get the general idea, it's good enough. So in the first test of our simulation, we used 7 shares of the London exchange market plus a risk-free asset. And so we have a problem with dimension 8. And we generated scenarios using historical data to compute the expected return C and the expected and the covariance matrix Q. To build larger problems, we used this data to generate artificial assets. So we made a combination of assets, and this was a new asset, and then we could compute, we could think of problems with dimension 1000. And in our tests, we solved this problem of 1000 variables in 1.5 seconds. And when we compared this with the classical approach, we got the same solution, but we took a longer time. Okay, let's see, at the classical approach, you solve one optimization problem. Okay, it's this problem, minimize this function with the reformulation, the KKT reformulation of this problem. Okay, and you solve this once, you're done. In our case, you have to solve a lot of convex problems. You have to solve a convex problem here, 2 convex problems in each iteration, and you have to repeat this many times, so it's a lot less slow. It's very slow. But what happens here with this problem is that this is a convex problem. This problem that this lower level problem is convex. So the KKT condition captures exactly this sense of minimizing this function. So in fact, the solution of this problem, the minimum, is equivalent to being a KKT point. So the classical approach should work fine. It's not unreasonable. This result was expected. We simply did this test to show that we could solve large problems with reasonable time, but for convex lower level set, this makes no sense. Okay, so this was just to formulate the general idea, but you can do this now for any multi-objective problem. Okay, so we compared the formulation. We generated 300 problems with 2 objectives, no constraints, and 4th degree polynomials, randomly chosen. In our formulation, here we only checked if we get a feasible point of our run. So if you get a Pareto point, okay? So we solved these 300 problems, and we saw what happens. Is it a feasible point? So in our case, we always find at least a feasible point. I'm not sure if it's the closest one to that decision. It probably is a good enough approximation, but it's a point on the Pareto frontier, or it is a KKT point for finding this problem, this minimization problem that defines a Pareto point. But in the classical formulation, it completely fails. For 1 dimension, it fails for 13% of the problems. For 10 dimensions, it failed for 84%, and for 20 variables, it failed every time. It never finds a KKT point. Okay. The third test set, we used this collection of unconstrained optimization problems, the Moré-Garbo-Hillstrom unconstrained optimization collection. It's something as 17 or something like that. I think we used 17 of functions from this collection, and it's a difficult collection. It's a collection of difficult unconstrained optimization problems, and when we combine 2 of these functions, we have a multi-objective problem. Okay, so we can, with these 17 functions, we can formulate 122 objective problems. In fact, we could explore this idea to multi-objective problems with using more than 2 objectives. But in this picture, we have the performance in these 2 objective problems. This black line here is the KKT reformulation. So this is the time you get, the time the algorithm runs, and this is the percentage of problems solved from this collection. So you see that the KKT reformulation, if you give it very little time, it will solve 40% of the problems. So it solves 40% of the problems in this amount of time. If you give it more time, it will solve a little bit more problems, 45%, but no matter how much time you give it to it, it never solves more than 45% of the problems. In our approach, if you give it little time for it, it will not solve any problem. But if you give it more time, you will solve 95% of these problems. So these are the 3 variations of the algorithm. The pink one is the original Fischer Friedlander algorithm. The blue one is when we use Lagrange multipliers only on the globalization step, but we use the Hessian of the objective function for subproblems. And the red line is the complete inexact restoration formulation, when we use multipliers for the Hessians and for the globalization. So you have an improvement on the robustness of the method. So it's not efficient for easy problems, but it's robust in the sense that it solves many problems. Okay, that's it. Let me show you some reference. This is the book again. This part on augmented Lagrangian methods, you can find this on this book published by Siam this year. This is the paper, our paper on inexact restoration. There are many references there for other inexact restoration methods. And if you are interested in this multi-objective formulation, You can find it in an extended version of this paper that you can download it at my website. That's it. Thanks.
Thank you very much. So I don't know if there is any last question. Either here or maybe in any of the other places. Okay, so I think we can finish here.
Okay.